Hi guys, good morning. Are you guys alive?
Yes, miss. Good morning.
When's the others? Can you help me to inform them?
Sure, miss.
Okay, let's wait for your friends for another 10 minutes. Sharp at 9 we start. Okay? Morning, guys. Is all over here? Guys, are you guys still alive?
Yes, miss.
Is
Hello, miss.
everyone here?
I guess so.
I know it's already near to your semester. Oh, sorry, it's your Raya break. But then, please, be a human. Don't be a zombie. So, how was yesterday, class? Any question you want to ask me?
No, miss.
Akbar, you said you want to open your webcam.
No.
Where is Kachin?
I guess he's sleeping. Let me message him or give him a call.
Okay, thank you. Who is 924? CSJ 924?
I think it's me.
Me is who?
June.
Oh, okay.
I think lah. I'm not so sure.
It's your own ID, bro. So Kachin is still sleeping, eh?
Probably.
It's okay. Tomorrow, I will do some free Hari Raya gift for you guys. Okay?
What? Gift?
Yeah, I have
Gift.
some gift. Yes, gift.
Yeah, you should give us more homework.
No lah, it's a gift. You should be grateful and appreciate my gift.
Sure, miss.
Yeah.
Okay. So yesterday we stopped until here. Am I right? Or no? It's just the
Yeah.
slides. So how many of you done with your yesterday surprise?
The homework.
Yeah. How many of you have already done?
Still left.
Oh, it's okay. Today I will give you add-on hand exercise.
Okay, miss.
Sanat don't sleep, eh?
No, no, no.
Okay, so we're going to proceed. So this is the simplest platform one circuit where we already involved with the inverter. Okay, so an inverter actually requires only two transistors. Okay, so this device usually we know them as a NOT gate. Okay, so the word gate is ambiguous, where in level 1 we know as a gate. Okay, a transistor also has a gate. Okay, so far, do you have any question for this slide?
No.
No. So next, this one. This one, note that the output signal came from power or ground, where your input is used to switch between the two of them. Okay, so the word gate is ambiguous still. Okay, so this one, can you see what will be the differences between these two? Can you see what is the difference between these two?
The 1 and 0.
1 and 0, what else? What else? Huh, what else? Huh, guys, what else?
So, open on the right, top right, close bottom right, instead of close top left and open bottom left.
Okay, if you see, you have a top transistor, okay, the above one, okay? Which one is the above one? So this one lah. This one is the bottom one. Okay, so these two things is connected to do different things. One connected to the power supply, another one connected to the ground. So which one is your power supply? Which one is your ground? Which one is the power supply? Anyone know?
The open one, I guess.
It's wrong. This one is your ground. G, sorry, ROUND, or we known as GND.
So the
Okay,
one with the blue is power.
this one is your transistor. This one, the triangle one, is your power supply with your PWR. Okay, it means that when you go into one, this one is closed. Right, this one we know is a high. Correct or not? Correct or not? But then when you have two inverter, your value would be 0. How come it becomes 0? How come it becomes 0? Ah,
Is there a NOT gate?
yeah, because you have a NOT gate. That's why your high, they will invert them into a 0. That's why you were producing a 0 as your output. Okay, so your top transistor will connect to your power supply, right? So when it was turned on, your input initially your input is 0, okay? And when it connect to your power supply, making it become 1, okay? And then when you connect to the bottom transistor, okay, your bottom transistor is connected to the ground, correct or not? So when you turn on, the input would be, and when you turn on your values, okay, at your transistor that is the bottom one, it should be 1. But when it connect to your ground, it making it become 0. That's why it turned off here. It become a low value. Okay? So far, do you have any questions? No?
No.
So how about you combining two signals? We can build a device that combine two input signals A and B to make a single output signal Q. Okay, it means that A plus B, you will get a Q. Okay, so how many possible patterns in the input are there? So this one you can see that you need to have the same low and low, high and high, and the other one is reverse around, which is low and high, high and low. So these are the possible inputs. Okay, if you have 4, you need to have at least 8 possible inputs. Why? Because each of these have possible, two possible what? Two possible value. So you have to times 4. So you will get at least 8 possible input. Okay? So how many possible output? You only have 2, which is high and low. Why? Why you only have 2 possible output? Why? Why you only have 2 possible output? Why you only have two possible output, guys? Are you guys sleeping? Hello?
No.
You're here.
Thinking.
Thinking. Okay, why you have 8?
Because there's only one output signal, Q.
Yes, it's this way. Okay? So, right? So, and two input, one output device. Okay, so this one is the examples. Just like I wrote just now, A plus B, you will get Q. So it means that you have one input, two input. Okay, that's why they say input A, input B. And then you undergo a process, you will get a Q as the output. Okay, so the question is, what is the possible for D to do and how it will be done? So what actually the D is? It's not. What actually is the D? Huh? Anyone want to try? Okay, this D, it can be your AND, it can be your OR, what else? And so on. Okay, as long as these two input undergo the D, it will produce an output. Okay, so what are the devices that are possible? Okay, there are 4 different patterns, right? For your 2 input signals. So each of your devices are characterized by 4 patterns. Okay, by a pattern of 4 outputs where each have one input. Your output Q either can be high or low. It only have 2 possibilities. Therefore, you're going to have 2 to the power of 4 equivalent to 16 different ways for you to combine the pair of your inputs A and B to make your output Q. Okay, generally, we can say that an input device has 2 to the power of n possible patterns. For example, you have 10 input device. So it means that you have to use 2 to the power of 10. Only then you can get the value of n. So this n is your possible way ways for you to do the combination of different pairs of your input. So far, do you have any questions?
No, miss.
Don't sleep, eh? Later I will give you calculation to do. Okay, so one of 16 possible devices where we start to count it from D0 until D15. Okay, if we count from D0 until D15, how come it becomes 16 possible devices? Anyone? Anyone know? My value here is from 0 to 15. 0 to 15. But how come this 0 to 15, it's become 16? Wasn't it only 15?
No, miss, because it's
Um,
starting from 0, I guess.
Yes, because we're calculating start from the 0. So when you count 0, 1, 2, 3 until 15, you're supposed to have 16. Okay? So they mentioned here there are 16 different rules for combining 2 inputs to make a single output. So one rule can go into the box D. Okay, where rule 0, Q is equal to low no matter what A and B are. Okay, so while rule 2, Q can be high where your both A and B is high, otherwise Q is low. So if both A and B is high, A, B is 1, 1. But then your output is also 1. So what exactly in the middle here? This is the rules that you shall know. Okay, so when they say rule 2, Q is high, A is high, B is low. So you put A is 1, B is 0, but you still get your Q as 1. How? What will be the process here? Okay, So each of these rules actually will define a different devices. Therefore, these devices we will refer them as a D n. Okay, where this n is equivalent to your numbers from 0 until 15. Okay, so each of device may be fully described by listing what output it gives for each of the input patterns. Okay, so this is the example of your rules one. Okay, so Q high when both A and B are high, otherwise Q is low. Okay, so now we set up the tables. Okay, we list all the input or output combination that is possible. Okay, so just now they said Q is high when both, so you put input, you put output. So input, you can separate it into input A and input B, and then you're going to have your output. Okay, so they said the Q would be high if only both is high, while others would be low. How do they know low? It's like this. You put low. Okay, so it means that you put H high in A, B is low, your output would be low. Okay, what else? What else? We have another low where your A is low, but your B is high. You're also getting a low. So there is another one. You have another low, but both is low for A and B input. That's why you get this table. But in order for you to get,
Miss,
Miss,
is this working like an AND operator?
yes, it's work like an operator. That's why you learn this kind of table. That's why you need to understand how do we get a truth table. Okay, based on the rules itself. Okay, so this is one of the examples. If they have more than one possible devices, so you can see that you're going to have, even though it's only have two inputs, you're going to have different output for 16 devices. Can you see? Each of them would be different. This one would be our D1 just now, right? Where our both A and B is high. Your Q will be high. Otherwise, it will be low. This one is our D1, correct? This is one of the possibles. So when we change into our binary mode, so low, I mentioned they use 0. High, we use 1. So that's why it become like this. So far, do you have any questions?
No, miss.
No? Easy?
Yes.
So what would be the possibility? So some of these devices are more useful than others because they implement the useful logical operations. Okay. So D1, D6, D7, D8, D9, and D14. Okay. So as you see here, all of this D would be your Q. Am I right? So we will look at D1. They said A is A and the B. That's why we get like this. Is this logic? Just like Mahruf said, D1 we are using AND gate. Is this logic? Now, how do we get 0, 0, then we get output 0? How come we get 1, 1, we get output 1? While we have 0, 1, we get 0. 1, 0, we get 0.
Miss, because both need to be high to get
Yes.
because the AND operator says if even one is not high or one, so it will give the low output.
Okay, so how about your D6? How come 0, 0, you get 0? 1, you get 0. But the two different input for your the values for your both input is different, you get 1. What is it? What will be this?
Because of the
Or
equation we have, uh, D6Q equals to A XOR B because of that.
what actually is the XOR mean? What is the mean by XOR? Okay, you say about XOR kan, right? So what is XOR actually?
Okay, Miss XOR is something like um um
Um,
so if the input is 1,
mm-hmm.
so it's like 0 0 will be 0, but 1 1 will be also be 0. I don't know how to explain this.
So XOR actually means for exclusive OR. Okay, so what will be the other name of XOR?
NOR?
NOR. XOR is a NOR. Sure or not? XOR is not a NOR. XOR is exclusive. Exclusive. Okay, where the input must be either A or B only. It cannot be both the same value. Okay, that's why you see that 0 0 must be 0. But if 0 or 1, you would be 1. And what will be the difference between XOR and OR? What will be the difference between XOR and OR? What will be the difference between XOR and OR?
1 and 1.
What do you mean 101? Okay, so if we say OR, it is an inclusive. As long as they have the number 1, it will get the value 1, like the D7 here. Okay, if you see D7 here, can you see D7? So D7 is the example of your OR. Why do I say this one? Because if your input have 1 inside, your output must have 1. If we compare to XOR, they only want the value that is different, which is it must exist 0 and 1 or 1 or 0. It cannot be the same value as your input. That one is for exclusive OR. Okay? Do you understand? But if OR, the other name of OR is inclusive. Inclusive, it means that all the information about input A and B that have value 1, it can be calculated as inclusive. But exclusive, you have to remove the one that have the same input like this, 1 and 1. So far, so good? Do you have any
That's
question?
no miss.
Okay. So, let's see to D14. D14, they said not AB, not AB. So, we go for your column D1. So, D1 is our N, correct? We have A and B, so we get 0 0 1. But for D14, it's a reverse of 1 1 1 0. But why? Why this one get like this? But still, they are using A and B. But why the value is like this? Huh? Why is that? Why is D14 is different with your D1? Anyway.
Because it's a not gate.
Yes, because we have a NOT gate. So what actually is the NOT gate? If we use a device, it is the inverter. Okay? Or you put A and B, you have a straight line on the top like this. I think this kind of logo symbols you already learned in previous class, right? The subject programming and discrete structure. Am I right? Guys? Are you guys alive? Or you need a 5 minutes break before we proceed? Guys?
I don't think so, Miss.
You don't think so? Okay, so we can proceed, eh? Okay.
Yeah.
So we call the most useful devices as a logic gates because they can be implemented as your logical operator and they used to for getting signals. So we have 6 more useful devices as we know, okay, based on the logical operation that they may use for, which is your AND, OR, XOR, NAND, NOR, and XNOR. Okay, so this is the truth table for each of the mentioned logical operators just now. Okay, so far, do you have any question?
No, Miss.
No. Okay.
No, miss.
So how are they built? So they are built from your transistor. The simplest to be built are your NOR and NAND gate, each of which constructed using only 4 transistors. Okay, still remember your transistor? Still remember your transistor? Okay, so a 2 simple input device using a NOR gate. What is a NOR? What is a NOR actually?
Is not or.
Yes, not OR. So if not OR, what will be the value?
It will be like opposite of or all of the values.
Example?
So 0 will be 1, and then 1 0 will be 0, 1 will be 0, and then 0 will be 0. Right?
So I have a simple question. Does your NOR gate same with your AND gate? Because they say here not A or B, right? So does this mean AND?
No,
Why no?
because um,
Like a
because
reverse.
for oh wait, no, sorry, it's correct.
Hmm? No. Okay. So your NOR actually have only one output when both input is zeros. Okay, so you can use AND gate to produce. You can produce AND gate using your NOR. Okay, still remember your De Morgan theorem? Still remember your De Morgan theorem? What is De Morgan theorem? Huh?
To find if all are true or false.
Okay, so for example, we have A dot B. Does it equivalent to not A dot not B and not again? How do you do this? How do you prove that these two things is actually the same thing? Here comes you use the De Morgan. So now I want all of you to do and prove me this is the same thing using De Morgan theorem. I give you 5 minutes and later I will choose the lucky person to share the working step. Okay? Okay, guys, how was your working step? Okay, let's get Tyson Yu to show me your working step to prove A dot B is equivalent, not A dot not B. When you
Yes, miss.
show me. Where? Are you guys done? It's okay. You guys will do it at home and share me your answer tomorrow. Okay? So next. This is when you have a simple two input device using a NOR gate. Okay, this device is simply to implement as it requires a 4 transistor. Okay, take note that your output signal comes after either from your power or your ground. Okay, so far, do you have any question? Guys, are you guys survive? So this
Yes.
is okay. So this is we increase again. Okay, so the different values just now we have 0, 0, and then you will get a not 1. So now we increase the value in 0 and 1, we get 0. So now we give a third possible input. Okay, then we'll still get a 0. And we have the last possible input, which is both is 1, and we still get 0. Okay, so I want you to do the De Morgan just now, this one, to show the relationship. Okay, so this dot, what does this dot mean? I want you to find out what is the dot means. Is this a plus? Is this an N or what? Okay, so next, and the others, any logic gate can be built from a combination of the transistor, but that is not the only way lah. As long as we start with a suitable set of logic gate, it is possible for us to construct all of the others by combining them. In fact, any gate may be built by combining several NOR gates if you know the logical equivalence. Okay, so you need to check back about your models and methods. Okay, that's why previously you learned a lot of theorem to do the proving. Okay, so however, this is seldom the most efficient way to do it. Okay, for examples, your OR gate can be built from two NOR gate, which you're going to have around 8 transistors. But for you to have the the efficient circuits, you can use NOR gate and NOT gate, which you're going to have only 6 transistors. So you already save around 2 transistors lah. Okay, so this is the examples of the logic gate symbol. Okay, so each of your logic gate have a special symbol when they are used in the circuits. So each have 2 inputs and output, except for your nodes. It only have 1 input, 1 output. Okay, so far so good. Do you have any questions you want to ask me? No?
No, miss.
So now I show you, this is the Logisim. Okay, Logisim. So you can see here you have different gates. Okay, you can try to use your end node. You can have your none. Okay, you can put your wiring. Okay, if you don't want this, you can remove. Okay. You can combine with all the outputs and try to stimulate. Okay, you can try and see what will happen to this logic gate. Okay, so if you have like this, what will be your output? What will be your output? So inside Logisim, you can choose anything that you prefer. You have your memory, you can have your arithmetics, you have your plexer, you have your gates, you have your wirings, which include your ground and your power, your transistor. Okay. So far, do you have any question? This is when you use your Logisim. You can simulate them like this. Okay. But my one, I didn't construct it to be so that it can run. Okay, so this is just an illustration. Okay. Do you have any questions as for now?
No.
Guys? No. Okay. So if you use Logisim, it will easier your life. Okay. Like this is the truth table for some two input gate where we combine different gates to produce an output. Okay. You have, if we have 3 columns as the output, so you need to perform one by one. Okay, which means that A and B we will put at the column N. Okay, so you have to make sure that everything is in sequence. Okay, gate inputs are connected to your transistor gates. Hence, when floating, your output is conflicted. Okay, so this one, if we have different input for none, NOR, and X NOR. Okay, so implementing logical expression A or B. So which one is the wrong one if you look at here? Which one is the explanation is wrong? If you notice, which one is the wrong one? Guys, which one is the wrong one? Guys, did you listen to me?
Yes,
Hello?
miss.
Which one of the explanation is wrong about the logical expressions?
The first one
Yeah, the first
Why?
one.
The first one,
Yeah, the
why?
first one, miss.
It's
should
all
be
gate
or
based.
Because
It's an OR gate. Okay. It means that you notice, it is an OR gate. Okay, so all of this you have to understand. Why does it say 1 times 2 input OR gate? Why? Can anyone explain to me? Why? Why? So let's draw. We have A, we have B, correct? And we use OR. OR is which one? Like this? Am I right? Or it is like this? Which one is the correct one for OR?
the first one.
Yes, the first one. So we have 2 input. That's why they said 2 input. Times 1 is 1 output. Okay? So how about this? And how come they have OR in the middle? Either you have 2 N input or you have 1 times 3 inputs N. Why it have 2 different representation? Anyone want to try? Okay, I choose Aisha. Aisha,
Yes, ma'am.
so you tell me, how do I draw for 2 times 2 input N? How do I draw? How do I draw, Aisha?
Yes, Miss.
How do I draw? 2 times 2 input n.
Mm, A and B to inputs.
Huh?
Especially we put A and B inputs for to get the output of the AND gate. And then
So I should put 1 like this and another like this. Is
mm,
it? Then how do I combine them? So how do I write? A, B, C, D. Like this.
mm, A, B,
Then
C.
how? Like this? Like how? Hmm. How about 1 times 3?
Mm,
How? So this would be the 2 times 2. Okay, if 1 times 3, 1, 2, 3. And how many logic gates that we have?
mm, mm.
Huh? So if we say 1 times 3 input, it means that you only have one AND gate where the AND gate have 3 inputs. Like this. A, B, C. A, B, C, you get an AND, then you will produce an output. Understand? Do you have any questions? Or you can put how? Like this. Can it be like this? Which one?
I
No.
think the second is wrong, right?
The second is wrong.
Is it?
Are you
But
sure?
like this, we will have like four inputs, right? Or I'm wrong.
We have 2 times 2, which is means that we have 2 inputs for a single n. But when we have 2 times 2, it means that we have 2 AND gate that have 2 inputs. That's why we draw it like this. Oh, sorry. It's like this. If we have 1 input, 1 AND, but we have 3 inputs. So the drawing is like this. That is how you read it. For example, you say A or B. A or B. Right? So A, 1 input, B is one input. So you have how many input? Two input. But how many OR gate you have? Only one. That's why you have one. Understand?
Yes.
Okay. Aisha, do you understand what is going on?
Yes, miss.
Anyone still have confusion about this one? Aaron? Okay.
Should be okay.
Okay. So this is the example on how we draw. Okay. So that's why just now I said we have one input and we have one OR gate which have two input. So we will have only one output. This one, just examples. Why the one just now that is not connected? It's because we use our, if you see, just now I draw is like this, 1, 2, and then I separate like this, right? But does these two being connected together to get A and B and C? No, right? So that's why we put it like this. We have one input. So this one input would be this one output would be our input for the second logic gate. That's why it's drawn like this. Okay? And then this one, we have 3 input and 1 logic gates. That's why it also will produce this one. So far, do you have any questions? Guys?
No.
No? Just now, just now, Mariam said my drawing is wrong. Right? Right, Mariam? You said my second drawing is wrong, right?
Yeah, like I still confused. Like,
Because why? Because I did not make these two things as this. These two is means that A and B, C and D is not equivalent to A and B and C. Understand? So these two is different meaning compared to this one. That's why Mariam said it is wrong. It is correct. Okay, what Mariam said about this is correct because the input and how we illustrate it producing a different value compared to this one. Okay, do you have any questions? Guys, are you surviving?
so we have two ways to draw, right?
Yes. If it have logical expression like this, you can draw as long as your output is the same as this one. You can draw in different way. Okay?
Okay.
Uh, as long as the output can be equivalent to these logical expressions. Okay? So next, this is the examples. And now I have one questions. This one and this one is the same. But why the illustration is different? Huh. Why the illustration is different?
Because you need to do BC first.
Yes, if in the second one, if we learn in a normal maths or the modern math, we need to prioritize the value that is inside the bracket. So that's why in your drawings, you have to prioritize the bracket first. That's why here they draw the B or C first instead of you are drawing it after the AND gate like this, the first figures. Okay, but still it have the same output. It just that you do the wiring differently because of your logical expression is different. Okay, so far do you have any questions?
No, miss.
Guys, okay, so this one, if we have a knot, okay, a knot. So Why does they not using like this and they put a not like this? Why they use a NAND gate directly? But still, it's will give the same meaning. Why? 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 Guys? Why?
What was the question again?
Okay, why they are using NAND gate instead of they using an AND with a NOT? Why? Huh? Why?
Because there's no
Because
single input gate.
because if we use and not, you're going to have extra transistor. Am I right? But if you use only none, okay, so actually it's not and, right? If we read this, not A, B, not A and B. So if we convert into a normal term, it means that we have AND gate, correct? And then we have a not in front. Still, we are having the same single output. Okay, we draw because we are solving the bracket first, right? So we put A, we put B, and we use a AND gate. And then we have a NOT, correct? So why does we did not use this step, but we are using this? Why we are using none instead of and NOT? Huh? Why? It is due to the efficiency because when we do a logic gate, we do your apa? If we want to construct an efficient hardware, we need to use as minimum as you can for the transistor. Correct? Why do we need to minimize the usage of transistor?
Is it like it will use more?
First, we want to reduce our costs. We want to empower the efficiency. We want to do some speed improvement and we want to give more spaces. When you have more transistor, it means that you will require a lot of spaces. You have to remember, as time evolves, your laptop, your phones, your PC, and so on, it's already evolved into a smaller version instead of we are having the big one. Okay? Because in the big one, we have a lot of transistor inside. But now, if you imagine, if in your laptop you have the same amount of the transistor with your computer desktop that is used in previous years, do you willing to bring along your laptop anywhere and everywhere? Guys, I'm talking to human. I'm not talking to the fish. I'm not talking to the wind. Please do response, guys. If you are not responding, maybe after Raya we change it back to physical class. Is it okay?
No,
No,
no, no.
miss.
Then please respond me. Don't
Okay,
keep on
miss.
silent. I'm asking you questions. If you keep on silence, maybe we'll do some heat up activities for tomorrow class. Okay?
Okay,
So
miss.
how about your ZOR? How about your ZOR? Why does it means 1 times 2 input ZOR? Can Nishimura explain?
Okay. Because like if you can see in the image, it's not connected.
Sure.
Yes. I mean, maybe.
Huh? Yes or no?
Uh, yes.
Yes, confirm.
If you said that, I'm not so sure. So yeah, confirm.
Sure, eh? How about others? Huh? How about others? Does what Nishimura said is correct?
I guess he's right.
You guess is right. Okay. So next, I want all of you to do these questions and draw the logic gate now and put them in tables and explain like this. I want it to be like this. So now all of you start to do it. I give you around 15 minutes, okay, to do it. Is it okay?
Okay, miss.
Or you want to do it in tomorrow class?
Can do tomorrow as well, miss.
Do tomorrow. Seriously?
Whatever you say, no issues.
Oh, okay. Then how about we try the first question first and then the other three we do in the class tomorrow.
Sure, miss.
Okay. So 5 minutes. I will choose 2 lucky person. Okay? Are you guys done? Nafi, can you show me yours? Nafi, are you done? Hello, guys.
Yes, Miss.
Are you
Hello,
done?
Miss.
Huh?
Done yet, Jen?
Not done yet. Why take so long?
Only the first one, right?
Uh-uh. Others?
Maybe. Done, I think.
Done? Rafi, why you took so long? Rafi is sleeping, is it? Rafi, are you sleeping? Okay, so can anyone share me the things you can put in the chat box for what you have done? Or you want me to pick up a
Miss,
name?
I don't have access to the chat.
Don't have access to the chat. Seriously? Let me check. Hmm. But later I will check it back about the setting. Okay. Then how about showing me your screen? But how come Sanat can write something, but others cannot? Zenji, can you type something?
No.
British?
Oh yeah, same here, Miss. The chat isn't available.
Oh, I know. Maybe did you guys use Segi College email?
Yeah. Yeah, Miss.
Yes.
It's weird though. Hmm. Did you accept my invitation for today class?
Like the one in the group chat you sent, right, Miss?
Uh, Not that one. That one is not invitation. That one is just a link. Because Sanat joined using the invitation that I give. That's why that's why he can post the message and so on. Right, Sanat? Sanat? Okay, so it's okay. So let's you guys share your screen. we let Aaron share your screen. Show me what do you do.
Okay, wait. Ah.
Don't cry. Oh, what is that?
I read it on sorry, I wrote it on a piece of paper, that's why. Is it this one?
What is your illustration? Logic gate illustration. Oh,
Oh, you wanted me to draw. Oops.
yeah lah.
Sorry, I did it wrong.
It's okay. So let's change to British.
I only have done the first one though, miss.
It's okay. Show me.
Okay. Can you see, miss?
Mm-mm.
So this is the first one. A and
Mm.
not B. So not gate and then output.
Oh.
Correct, miss.
Okay. How about you right click at the B, you remove the N,
Which one? This one?
the NOT gate. You remove the NOT gate.
Okay, wait. Okay.
Okay. You right click at the blue line for B, show attributes. You cannot put an N. Or
Where, miss?
you click the N gate.
Okay.
Click the N gate. Why you want it like that? Sure. Look at the bottom.
Which one, miss?
The type selection and gate. At your left hand panel.
This one, miss.
No, go to the left.
The left, this one.
No. Okay, wait, I show you. Wait, I share my screen.
Right.
So can you guys see my screen?
Yep.
For example, this is my AND gate, right?
Yeah.
Okay, this one is my AND gate. Okay. So this is my NAND gate. Can you see this panel?
Oh.
So if this an AND,
Oh. Yeah.
so does this means that A and not B?
It's
Or
like, yeah,
you
A not B because it's negate.
or we need to put a NOT?
Doesn't both
Which one?
work, miss?
That one you have to try.
Oh.
All of you, I want to see you guys do this logisim tomorrow. Okay, so please bring your laptop that already installed with your logisim. So
Alright,
far, so good.
miss.
Any question you want to ask?
No, miss.
No. In Microsoft Teams, can you guys access the general part?
The general part meaning what, miss?
For example, right? Wait. Can you see my screen for the Teams?
Oh, yeah.
Okay, so if you go to Silicon to C, click this one. Okay, you go for generals, you go for files. Did you see these three things? It's not including the recordings. Did you see the reference books and course brief?
Yeah.
Did you see? Or you guys did
Oh.
not see this?
No, miss. I don't think I have that.
You don't think you have that, eh?
Yeah.
How come you don't see it?
I think we need the code to join the team, maybe?
Yeah, there should be a code, miss. Is there not? To enter?
Wait, wasn't
Yeah.
all of you already inside these things?
No, I don't see that.
You don't see the channel here.
Yeah.
Let me see, manage my team. Members. Oh, I already have 8 people inside. See? Is yours? Is you guys yours? Oh no.
SCS.
Off. Oh. Because I don't see any pending requests for the channels. I only have general and undergo for the files here. This guy is supposed to be able to check for that one. Can you guys access it? Or cannot at all?
I can't.
Yeah, same here, Miss. Wait, I show you my screen, Miss. Wait,
Okay. Let's stop staring.
this is my one, Miss. Wait, I don't see any.
Try and search. Eh?
Don't have, Miss.
Give me your student email.
Okay.
That one if you use the Segi group one or the Segi for you one.
Segi for you.
Sweet.
Yeah, same for me, miss.
You also cannot access.
No, I can't.
Me too.
What else? Provide me your email. Ah, sorry. SC, Miriam, you go first.
Email?
Student, Segi email.
Okay.
CSJ24. Host one is 24000706. Rafi. Rafi, try and see whether you can access or cannot. Planet is here already.
Can I give you mine?
Wait, 548 is who? I cannot find this one. Who is SCSJ 548?
Name is.
The one I cannot search. GG. Oh my god. Five, four, eight. Try and see whether you can access or cannot.
Miss, is this the same issue it says account not linked?
I don't think so. This one is for your request.
Oh, okay.
Let me check. True. Okay, I tried to give you guys this link.
Yes, miss. The link you gave in the group, I rejoined with that link, but that wasn't working. So I went to my Outlook, and there was an email there for this meeting, and that link was working only.
Try everyone click this link that I sent inside the group. Can you guys try and access? And you guys join the link for the general in Teams? Rafi?
Same, miss.
Fine, miss.
Because I did not receive any request.
Okay, miss. When I open the link, it just shows me journal chat.
Journal chat.
Yeah, same.
Yes.
General?
It's just the question you posted yesterday for relation between circuit and electricity.
Yes, same here, miss.
So in general, you have the post lah, like this. This one. Oh, sorry. I didn't share my screen. Sorry. So this one, you only see this one, general and post. Right.
Yes, yes.
Click on the files. Do you see the files? And you shall be seeing the files, course brief reference book. Do you see that?
No, miss, we can't see all
It,
this.
it only shows us the post. It doesn't show us the option to change to files.
Oh, okay. Start sharing. Okay. Yeah. Try to refresh and see whether you get the link or not. Oh, I copy my link and share it to you guys. See whether you guys can access it. Try and see. So it's 924.
Me.
So now can you guys access it? Can you see this one? This file? No? Because I will upload everything here. Only your assignment I will post inside your, how is it? Inside your Spark. Lots.
Yes, miss. I guess it's working.
It's working, eh?
Yes, miss.
It's a bit different, but yes, I saw it. Yes.
So as for the course file, I haven't uploaded anything yet. Okay. So all of you can see lah, everything here. So it means that you can see my course brief, you can see my course file, right?
Yes, but not in Teams.
Yes,
It
miss. It
shows
says the folder is empty. It says course brief, but the folder is still empty.
Yes, the course is empty. The course file is empty. The course brief is also empty. I haven't uploaded anything yet. Okay? But the recording, I already uploaded inside your YouTube. Okay, already put the description inside the combined one. Okay? So, let's continue, finish the part B. And we have another one is part C before we go for numbering system. Are you guys still okay to proceed?
Yes, miss.
Okay, so what and if we don't have our expressions, what if we don't have our expressions? Okay, it means that we have to employ the sum of min terms procedure to create an expression. Okay, so you have to understand that if you don't have the expressions, how do you want to build your circuits? It maybe makes you more efforts, wasting more times for you to design or to do a wired circuit. Okay, but then what if we know what output we want and can draw a truth table, but we don't have your logical expressions? How do we work on? Okay, so one way to deal with that is to employ the sum of minimum terms to procedure to create an expressions. Only then you can create a circuit. Okay, so that is for the chapter 1B. So far, do you have any question for chapter 1B before we proceed to 1C? 1C, we have 52 slides. Okay, this one is just a recap for your logic gates, symbols, logic gate truth tables. Okay, we do some recap. Okay, so all of these questions, you need to do it tomorrow. Okay, so chapter 1C, we go for platform 1 logic gates. Last lecture, we learned about a NOT gate and NOR gate. Okay, may be built from your transistor. So NOT gate, we only have one transistor, one input and one output. For NOR gate, we have two transistor pair. Okay, we have two inputs and one output. So today we're going to look at this. How do we use this and other gate to solve your problems? By performing arithmetic operation and arbitrary truth table NOR gate. Okay. So still remember why I assigning platform 0, platform 1, platform 2, 3, 3.5, and 4. Still remember why? Still remember why? Because we are covering for the tenable models, okay? So for platform 1 is more on devices where they will provide several devices that may be used in the constructions of your platform 2. So these devices may be built directly from your transistor, but to make it more sense to start by looking at them as a logic devices that are constructed from your logic gates. So so your gates may be used to build your circuits. To build your circuits have few types, okay? You can be the control circuits, arithmetic circuits, and logistic circuits, and also a stateful devices. Okay, control circuits is used to gating, arithmetic for adders, logistic for decoders and multiplexer, and the last one is for the registers and memory cell. Okay, so how do we use gate as a control? So we put a switch between your signal. Okay, so this logic gate will become your switch either on and off or high or low. Okay, so for example, a box with two input A and B and a single output X. Still remember the boxes that that we have last chapter? The one that we have the one that we have 1, 2, and then a boxes that have D and we have output. So this is the box that they are mentioning here. Okay, so this output is our X. This is our input A and B. For example, A is 0. B output is a B. Otherwise, output is 0. What does that mean? Huh? B is your signal data. Okay, any signal data, any bit numbers. Okay, so when A is low, output is B. Otherwise, output is equal to 0. So your output would be X is equal to B. So how does this process from A and B, it will produce a big B here. Okay, but others, you will put it as a 0. How? Here comes you use the control gating. Okay, so how do we do this? So for example, you need to draw your truth table. So if A is high, so that's why you put A is high. So you need to have 2. Why? Still remember we have the 4 possible patterns for input. Still remember? So you have to have high, low, high, low. So this would be different is high. This one will be low. This one is low. This one is high. So they have their own partners. All of these 4 must be fulfilled. Okay. So for B, X is equal to B. So this is X. Okay. So X. Otherwise, X is low. So you put your X is low. So it means that whenever that your A and B having a low, it means you will produce a low. So you have to see in which of the possible input have low, the LH, the LL. Okay, so you have to implement in here. Okay, so X is equal to B. If your X is low, B is low. And this one you will get the answer already. Am I right? Because A is high. Only then your X will become B. Understand? Do you have any question for this one? Guys? Do you
Oh,
understand or not? Or you want
understand.
me to repeat? Okay, what if they said B is low, X is equal to A. Otherwise, B, otherwise your X is low. How? How do we construct the tables? So A, B, X. So B is low. X is equal to A. Otherwise, X is equal to low. Huh? How? Huh? How? How do we do this, guys? If you say you understand, it means that this one you can solve. Huh? Guys,
A and X is a low.
A and X is low. Sure. I put low. Then, what else? How about this? Huh. What else? So we have another one. Our B still is low. What will be the possible input?
X is low and A is high.
Is high. X is high. And then what we get? What else that we have? Huh. How about our B is high?
A
So
is
A
high.
and X, huh?
High.
High. How about our our B is another H? Sorry. How about our B is another H?
A is low.
A is low, so B is equal to low. So can you see the pattern here? Can you understand? Okay, from this high and low, how do we convert into a binary? Do you remember? 1 is what? 0 is what?
Think low is 0 and high is 1.
So we follow the first one. Low considered as?
0.
Oh, sorry. Low, we put 0, 0, 0. Okay, then H is
1.
1, 0, 1. Then 1, 1, 1. 0, 1, 0. Okay? Do you understand this one? So actually, when you use low and high, it's exactly reflecting your binary value, which is 0 and 1. Okay? So far, do you have any questions for this one? No? Okay. So, how do we do this? Rewrite the truth table in order so that we can compare it with the standard gates. Okay, how do we rearrange it? So usually people will do the arrangement like we start with 0, 0, 1, 1. Still remember the formula of the conversion tables that I teach you during our last week class? Still remember? We have A, we have B. Still remember the patterns? 0, 1, 0, 1, and then we have 0, 0, 1, 1. Still remember? So use that pattern inside this one. This is the standard how you arrange them. Understand, guys?
Yes.
Okay. In order for us to start, okay, you have to understand that if we start, we have A and B, we will have 0, 1, 0, 1 and 0, 0, 1, 1. What if we only have A? What do we have? 0 and 1 only. Understand? Guys? Still remember we have 2 to the power of 2, which equivalent to 4. That's why we have 4 digit here. Okay? Guys, are you alive?
Yes.
Yes, miss.
This is why last week I introduced you the conversion tables, the patterns. So this is where you will need to use that things. Okay? So next, how about the second example? How do you want to draw this? When A is low, X is equal to B. Otherwise, X is equal to 0. Huh? Guys? Huh? Do you understand why does they produce this thing, this table? Do you know how they produce this table? Because they are putting the information like this. A is low, B is low. Sorry, A is low. So you put 2, 0. Okay, so X is equal to B. If B is 0, so X would be 0. So beside you have a low, it means that the A would be high. Correct? Guys?
Yes,
Guys?
miss.
Survive? Okay, since you don't have question, let's proceed. How about we do the restating? Okay, restating, it means that we add another column to the truth tables. Okay, and do the rejig. Okay, so when A is low, X is equal to B, otherwise X is equal to 0. So we put a negate in front of your A. Why do we put a negate? Huh? Why did we put a negate? Why? Why do we put a negate? So go back and find out why do we need to put a negate and why do we have to have the restating, okay? So this is the device that we need is made from NOT gate and AND gate, but Logisim provide a shortcut. So this shortcut I already teach you just now how to change it, right? You can just click at your gate and then go to the left panel and check which of the negate, which of the, what we said, for that one, let's see. Okay, so you see here, right? You click on your gates and you see at your label here, at your left pane. So you have negate 1. It means that the first one will be a negate. Okay, if you have negates 2, it will put a negate there. Okay, if you want to be a negate 3, it will be in the middle. Negate 4 is like this. Negate 5 is like this. Okay, so you can put different type of negate at different of the input. So if you put all is negate, make sure that all of your input have the value A or B or C. Okay, understand? So next, by wiring the two devices to input pins A and B and compare their outputs to all possible combination of A and B. Okay, so how come your A, B will get a 0 as the outputs for both gate? Does these two gate brings the same meaning? Guys, does these two gate bring the same meaning?
Yes.
Why yes? But the representation is different. Huh. Your friend must be asking me, but miss, the what we say, the representation is different, miss. How come it's the same? Huh. How come it's the same? British, can you explain why? Why Nishimura said it is the same?
Mm,
Why does Nishimura say those two gate meaning the same thing?
because like there's the NOT gate there, miss.
Yes, because how does they represent the NOT gate? Okay, if we follow the first one, this one, yeah. if we follow the first one like this, it is a not A. Okay? And B. But for this one, we have the also A, but we put a not directly to the AND gate. Instead of we are having another simple, another not gate here. This one is the shortcut provided by your Logisim. Can you see this one? You already mentioned Logisim provide a shortcut. Allow us to do the invert at a NOT gate, one or more inputs of your AND gate. Understand? That's why just now Nishimura said it is the same. Okay? So far, do you have any questions? No? Okay. So, now, tell me, why does these two things become one when your input A is 0, your input B is 1, but why your output is 1, not 0? I want Tai Zhenyu explain. Tai Zhenyu.
Because it is saying not 0, right?
Uh-huh.
And then the A is become 1.
Is it? Okay lah. So, let's break down. Zhenyu, can you tell me the first row here? So this one would be how much? 0, right? But after not gate, it become?
1.
Okay, 1. So B is 1.
1.
1 and
1 is
1, you
1.
become 1. Okay, how about Maru? Can you explain this part? Maru,
Yes, miss. Which one?
this one. Huh. How do you explain this one? This one is 0. This one is 0. Right? This one is 1. 0, not
0 will be converted into 1,
okay. This one?
and it will stay 1.
Okay. This one is N. So we will get 1.
1.
So do you guys understand this one, what is happening?
Yes, miss.
It's very
Yeah.
easy, right? Okay. So let's go to the next questions. Okay. This one. Do you understand this one? Why it gets 0 even though the value is 1 for both input and output? For both input?
Yes, miss.
Yes.
Yes.
Mariam, do you understand, or you want to you want to ask me questions?
I think yes, it's the same as previous one.
It's the same. Okay. So gating, what we're doing is modifying your signal B based on the value of signal A. We can use the truth table, but there is an easier way to work out what is required because different type of logic gates are used for different purpose. Okay? AND gate, you drop the B. Okay? Or pass it through. AND gate, NAND gate, you raise the B or invert it. Okay? OR gate, you raise your B when your A is equal to 1 or you pass it through. Okay? So this is the explanation of each of the gate. Okay? So gating is an alternate labeling. So think of two inputs as control and data. Okay, and it means that you drop your data or pass it through when your CTRL is equal to 0. Your control is equal to 0. You need to drop your data. But if your control is equal to 1, you need to pass it. Do you understand? What does it mean? So you have two input, one as control, one as data. So it means that if your control is 0, you have to drop your data. So your data would be 0. Understand? Because you are using N and you will produce a 0. Understand, guys?
Yes, miss.
Okay. So next, we can use gates for control. If you can work out what gates are needed to implement the following, okay? So if A is high, X is equal to 1, otherwise X is equal to V, as V block B. Okay? So we need to use the logic gates to control our data signal based on your condition, whether it is true or false. Okay, remember that you need to invert one or other of the input in order to implement the functionality. That's why I really want you to understand about this. If you don't understand this one, your truth table would be wrong. Okay? Okay, guys. Still
Yes, miss.
surviving. So, next. This is the answer for the previous slide. So, this one lah. Or I hope you able to understand how does this table can be produced. Okay? So, our class and at 11:30. Am I right? Do you need to have a 5-minute break? Okay, we have a 5-minute break. Then we proceed again until 11:30. Okay.
Okay, miss.
Okay, so let's resume. Devices with two or more outputs. Okay, so when a device has two outputs that depends on the same input, we can draw two truth tables. Okay, but it is easier for you to create a single truth table with two output columns. Okay, for example, instead of you drawing single column, single table like this, okay, you can combine these two. You can combine and become like this. Or if you still remember in previous chapter, in chapter 1b, I have shown you A, B, and then we have D0, D1, D2. Okay, that one is the combination of more outputs. Okay, this one is only you have two inputs. Okay, but we have two outputs only. Okay, so far do you have any questions? So it turned out that this is the truth table for a single 1-bit adder, where a device that adds together the two 1-bit numbers and give a 2-bit result. Okay, the output are independent of one another, so we can build two devices and give them the same output. So example for this one simple adder. Okay, a device has two input and have two outputs, S and C out. Okay, that have the following truth table. Okay, the effect of this device is to add the two 1-bit numbers A and B, giving them the sum on the output S and the carry out at the output C, where we know as this as a half adder. Okay, so for example, 0, 0, we have 0, so we don't have any carry outs. Okay, but if 0, 1, okay, if 0, 1, our S, okay, our S. Okay, guys. So S is our output. C out is your carry out. Carry out. This carry out, for example, we add 1 plus 9. So we will get 1 here and put 0. So we will bring down the 1 below. So this would be the carry out. Okay? So same goes with binary bit. Okay? If you put 1 and 0, when you add it together, do we need to have an carry out in front? No need. So we just put it as a usual like this. So that's why your 0 and 1, okay, or 1 and 0, you have no carry out. Okay, your output is only 1. But why does you, when you add 1 and 1, you get 0, but you have a carry out 1 here? Anyone can explain? Guys, this one is important, eh?
Miss, because 2 in binary is 1 0.
Yes, because in binary, we cannot exceed the value of 1. If we have 1 plus 1, supposed to be is 1, 0, right? Or in our decimal place is 2. So if 2 we convert into binary, it's supposed to be 10. So that's why you have a carry out here. So you put a 1. Do you guys understand? Do you have any question for this one? It means that whatever your value is cannot be more than 1. If more than 1, it needs to have a carry out in front. And the value as the output would be 0. Okay? Do you have any question, guys?
No.
No, miss.
Simple, eh? So next. Okay, a simple adder does not do enough. Typically, we want to add together two n-bit numbers where your n can be more than 1. And to do this, we need to have a carry from one column to the next. Okay, for example, this one. Okay, for this one, 0 plus 1 is 1. 1 plus 1 is 0. Uh-oh. So are we bring our 1 here in front? Do we have a carry out here?
Yes.
Huh? Yes. We have our carry out. And then we have our carry in. How do we mean by carry out and carry in? What is the difference between carry out and carry in? Okay, for you to understand, carry out is you carry the value from the previous bit. Okay? Previous bit. If you have carry in, what is carry in?
Add one.
Add 1. Yes. So, you will add 1. So, but 1 plus 1 plus 0. Why you still get 1? Why you still get 0? Didn't get 1? Why? 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 Because 1 plus 1 is already exceed the value of 1. Am I right?
Yes.
And then we should bring our 1 in front. Am I right? So that's why you have 1, 0, 0, 1. That's why they say each of your column produce a carry out and each needs to be carry in. Okay? So far so good. Do you have any questions?
No.
No.
I
Why?
can
Why you want to
understand
cry?
like no, I'm crying, but like why it's like 1 plus 1 is 0.
Okay. Why 1 plus 1 equal to 0? It's not equal to 0, Mariam, actually. It is equal to 1, 0. Okay. Binary, how many numbers, how many representation? Only 1 and 0, right? Correct or not?
Yes.
So the maximum value is only 1, correct or not? If we
Yes.
put in our conversion table, still remember our conversion tables? This is our bin, this is our decimal. We have 0, 1, 2, 3, 4, 5, and so on lah, correct? Our bin, 0, 1 is 1. Then if we have 2, is 1, 0, correct or not, the value?
Yes.
So if you 1 plus 1, how much you will get? 1 plus 1. Sorry. 1 plus 1. You will get 1, 0, because this is in binary. You cannot have the value more than 1. If more than 1, you have to carry another 1 in front. So that's why you have this one. Understand?
Yes, yes, yes. Thank you.
Okay. So far, do you guys have any question for this one? No?
No.
Okay. Next. This is the full adder job. Okay, so 3 inputs deal with A, B, and carry in, and 2 outputs where you have your S and your C out. Okay, so this is your S, this is your C out, this is your C in. Okay, so C in is 0. So A and B. A, B, you will get output 0. Do you have any carry out? No. Do you have any carry in? No. 0 plus 1, you get 1. Do you have to have any C out? Carry out? Do you have to have any carry in? No. Okay. So how about 1 plus 1? 1 plus 1. Okay, 1 plus 1, your output will be 0. You have to carry out a 1. Okay, and then this one, you need to carry in into the in front. Okay, so it will stay like this. So 1 plus 0 plus 0, you will get output as 1. So far, do you understand? Guys? So,
Yes,
Yes.
yes.
Yes,
it's
Miss.
actually written like this: 0, 0, 1, 1, 0, 0, 1, 1. They need to add with your 0, 1, 0, 1, 0, 1, and sorry, 0, 1. Okay, so when you add up, start from in front. Do we have? Oh, sorry, I written it wrongly. So, for example, we have 0 plus 0. Do we have any add in? No. So we have 0 here. Then we have 0 and 1. Do we have add in? No, 0. So we just bring our 1 here. That's why you get the S like this, 0, 1. Okay? And then we have another one, 1 and 0. 1. Do you have carry in and carry out? No. Okay? It's like this. But if you go to the 0, you have 1 and 1 like this. This is your value 0. You have to carry out a 1 here in front. Correct? But if you see the next bit is 0 and 0. So this one is already became your carry in where you need to add with 0 and 0 you will be this one. Understand? Guys?
Yes, miss.
Oh,
Yes.
guys. Are you guys surviving? Okay? So that is as simple as that. So, next. Why do we need to look at a simpler adder? Because when we need to construct a full adder, we have to construct them from triple adders and with and OR gates and explain why they are called half adders. Okay? So the circuit does the job and easy to understand. It means that why you need to learn a simple adder? Because you need the simple adder in order for you to construct a full adder. Okay? So devices with 3 inputs. Once again, we define a 3-input device either by writing a Boolean expression or you create your truth tables. So far, do you have any question about your Boolean expressions and your truth tables? Okay, so if we have a Boolean expression, it will be very easy for you to create a device because you only need to change the Boolean expression into a logic gate that have been expressed inside your expressions. But if you don't have your Boolean expressions, how do you do it? Okay, that's why you need to understand the statement that have been taught to you previously. So based on the statement, you need to create a truth tables. Okay, so if we have 3 inputs, it means that you shall have 8 rows. How do we know it's 8 rows? Here comes your 2 to the power of 3. This 3 means by your number of input. Understand? If you have 3 inputs, it's 2 to the power of 3. If you have 8 input, 2 to the power of 8 as your number of input. Understand? Only then you can construct how many rows that you shall have. Okay, guys? Understand?
Yes.
Any question? Or you guys want to collapse ready? Okay, it will have 4 columns, 1 for each input and 1 for each output. 2 to the power of 3 is equivalent to how much? 8, right? But how come we only have 4 columns? And you're going to have, again, what?
3 input and then 1 output. That's why 4 column.
Good job. It means that you understand what is going on. So how do we draw it? So you shall draw your tables going down like this. Have 4 columns, 3 input. Okay. A, B, C output. And then you have how many rows? 1, 2, 3, 4, 5, 6, 7, 8 row. Correct? So this would be the sequence of your truth table. Okay? So it would be 256 different truth table like this. It won't always or be obvious on how to implement your circuits. Okay? So implementing arbitrary function, there is a method for you to implement any n input of Boolean function from the truth tables. It's just a few simple steps, okay, known as your sum of minimum terms. So it relies on the fact that any Boolean function, no matter how complex it is, it can be implemented using only AND or and NOT gate. It will provide a set of simple rules that can be followed. So the sum of your minimum term methods seldom results in the most efficient implementation, but if the method is applied correctly. If you apply it wrongly, your efficiency would be going very, very bad. Okay? So sum of min terms, it is an observation. Any logical function may be implemented a combination of your AND or and NOTs. If we know that the desired output for a particular patterns of input is 1, we can work a circuit that is guaranteed to give an output of 1 when your input pattern is presented, and 0 for any other input pattern, just only when you use the combination of AND and NOT. Okay? If we create a set such circuits and or their output, together we can guarantee that your combination will give an 1 output for all those input pattern that requires it, and a 0 for output for all of the input patterns. Okay? So this one is the examples. Okay, we have a device that has 3 inputs X, Y, Z. Suppose one row of your truth table tells us that the input should be X is 0, Y is 1, Z is 1. So the output should be 1. So how do we use your expression to match with this row? Using not X and okay? So you can see that they use a not X and they do the and Y and they use and again with the Z. Okay? So if this is the only input pattern that should give an output of 1, we have solved your problems. Okay? So this is the examples. Okay, just now they mentioned that your X is 0, your Y is 1, your Z is 1. Okay? So your output would be 1. Others output will be 0. So this is the circuits that implementing your information here. Okay? Okay? So, do you have any question up until now?
No, miss.
No. Can we? Okay. Can we proceed? We have another around 18 slide. 18 slide. 18 slide to go. Okay. So example 3, what if there is a different pattern of inputs X, Y, and Z that shall result in output of 1? Say that the pattern is 1, 1, 0. Our circuit cannot deal with this, so we need to devise a different circuit to do so. So this one. Okay? The example. Okay, so the circuit here derived from a software package where you need to understand that the bright green wires is a high voltage, which represent 1. Dark green represent low voltage. Okay. So far, do you have any question for this one? So what if there are several patterns that have input X, Y, Z that shall be output as one? So we can deal this with creating a set of expression using not and and. So one of each input pattern requires an output of one. Okay, so you have to put, suppose there are 4 input patterns. Okay, just now they have give you the output patterns 001, 010, 011, and 110. All of these 4 will have a produce output 1. So we will end up these 4 expressions. Therefore, 4 circuits has been created. So each of these known as min term, but the device supposed to be only have one output. So how do we combine them? Okay, so you shall put them like this. Okay, so each line of the table known as a min term, it yield 1 on only one single combination of your input values. Okay, like this. So each of it, you have to create one for yourself to see what will be the difference. So simple. Only one circuit can output a 1 for a particular input, and the circuit only output 1 for a 1 for its own input pattern. So we take the output of all 4 circuits and combine them using OR to give a single output. Okay, we use all of that one just now that you have create for each of the row. Okay, you combine them using an OR. Okay, combine them like this and OR. You will produce a full circuit like this. So this whole circuit means that sum of min terms where you combine 1 min term, 2 min term, 3 min term, and 4 min term. Okay, so far you have any question for the min term? Okay, back to the full adder. Okay, this device can be implemented using a sum of min terms approach. 2 circuits, each based on one of the 2 output columns. Okay, so gates are leaky abstractions. The real electronic devices do not behave the same as your Boolean operators, where your floating inputs may lead to conflict. There will be time delay between your input and output. They will take up your spaces and they must be connected to one another by wires, and they also requires power. Okay, the complexity of circuit is constrained by size, layout, power consumption, and time delay. And some of those functions that we can specify are not practical to be implemented, and sometimes it may not work as you expected. Okay, so this is how we calculated how many transistors that we will need to use. Okay, for example, gate count. You have 1, 2, 3, 4, 5, 5 gate, correct? But you have 2n. Okay, that's why they do the 2 times n. 2n, you have 2 XOR, you have 1 OR, equivalent to 5 gates. So transistor pair. Okay, so 3 pair used in each n. 3 pair used in each n, it means that you need to times 2 times 3. Okay, and then you need to add with 2 times 4. Why 2? Because your XOR only use 2 pairs. Okay, 1 times 3 because you use only 1 OR gate, where 1 OR gate equivalent to 3 transistor pair. So you add up all of them, it means that you are required to use 26 transistors. Okay? So, cost of a full adder from scratch, it will be worse than your 2 half adders, 3 AND gates and 2 OR gates, which equivalent to you times with 5 times 3 transistor pairs, plus whatever is needed for 3 input XOR, which is cost more expensive. Okay, therefore you need to structure it properly. Okay, structuring would be useful and it can save your budget and also your spaces. Okay, so far do you understand? Do you have any question for this one? Guys, don't silence. We have 4 more slides. So, cost of a full adder via min terms, a full adder can be implemented as 2 sum of min-term circuits. Okay, so we can try you to use one of this, which is a single bit or versus multi-bit devices. So we started off by looking at devices that use to manipulate single bit values, okay, where each device works on one or more one-wired input signal, each of which carries a one-bit string. Okay, but you have to remember your aim is to build a device that can manipulate many bits in parallel. So when we say in parallel, all of the signals can be passed along several wires. That's why you learn about series, parallel, and so on last chapter. Okay, still remember? Okay, so each of these devices will work on one or more n-wired input signal, each of which carries an n-bit string. Okay, so that's all for today. So far, so good, guys. Are you guys still alive?
Yes, Miss.
Yes,
Okay, that's
Miss.
all for today. See you tomorrow, and I will give you some calculations for tomorrow. Please remind me, okay?
Miss.
Ah,
Is it possible to share the slides on Spark or on the WhatsApp group?
I will share you the slides inside the Teams. That's why I request you guys to give me your student email. So everyone can get the link. Okay?
I already gave you, but it was like personal one. I just changed it, so I'm still not able to see the slides on.
Okay, I will share it. If you can't access, you tell me, okay?
Okay. Thank you.
Okay. Bye-bye.
Bye.
See you guys tomorrow. Please don't be late. Those who are late, we're going to have some entertainment slots, okay?
All right, Miss. Thank you, Miss. See you.
Okay. Bye-bye. See you guys tomorrow.
Thank you, Miss.
Welcome. Akbar Rafi.